This worksheet has 3 problems that's going to give us a chance to practice these radioactive decay type problems. The first problem that we're looking at here looks pretty similar to the problem that we just did in the section 20.3 notes. It's telling us about a piece of wooden artifact. This is telling us that it's 2,300 years old, so that's our time. 2,300 years old. It wants to know what the carbon-14 activity is. So that's going to be N1 in this equation that we're going to use. The natural log of N1 over N initial is equal to negative KT. Fresh cut wood has an activity of 15.2, so that's our N0. And the half-life, there's a typo on here. The half-life can't be in inverse years. The half-life is 1.21 times 10 to the minus 4 years, which we're going to use that to figure out the value of the rate constant K. So we don't really need to know the half-life. What we need to know is K, and we're going to get K from the half-life. So we're going to use this equation right here, and first thing that we're going to do is multiply both sides by K, so we get that K moved up, and then we're going to divide both sides by T1/2, so we're going to get the T1/2 moved down. And we are going to plug in 0.693 divided by the half-life, 1.21 times 10 to the minus 4 years. And this is 5727 years to the negative 1, inverse years. It's a little bit different than the number that was given to us in the previous problem. Just using less sig figs, I'm sure, is the only difference there. So we're pretty ready to solve. We know our initial N, we know our value of our rate constant, and the time for this problem, 23,000 years. So we're ready to just plug stuff in. We're going to get the natural log of our unknown N1 over N initial, which is 15.2. And that is equal to negative K, 5727 inverse years, times our time, 2,300 years. When you're solving problems like this, just be a little bit careful about your units. Make sure that the units are consistent. So we are going to get the natural log of N1 over 15.2 is equal to negative 5727 times 23,000. I see I lost a 0 right there. Negative big number 131721000, no units on it. To deal with the natural log, we're going to take the inverse natural log, so we're going to end up with N1 over 15.2 is e to the negative 131 blah 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 blah, which is, oh, what? More than my calculator can handle. That's too bad. Unsolvable for me. So this is how we would solve it. And then we would want to multiply both sides by 15.2. I wonder if I've just maybe done something wrong with my math. Let me just double check my numbers here. 0.693 divided by 1.21 times 10 to the minus 4. That's 5727 years multiplied by 23,000. Yeah, my calculator just says overflow. So maybe if you have a calculator that was not made in the 90s, you will be able to solve this problem. But this right here is the answer that we would get. Moving on, problem number 2. Iron 59 decays to cobalt via beta emission with a half-life of 45.1 days. Write a balanced nuclear reaction for this process. So let's start with that. Iron 59 decays to cobalt, not carbon monoxide, cobalt via beta emission. So let's fill that in. Let's see what we're going to get here. First, we need to look at a periodic table and see what the atomic number is for iron. Iron is atomic number 26. And what's the atomic number for cobalt? That is 27. And let's take a look at our beta emission. So we're emitting a beta particle, which is also known as an electron. And there's its information. So that tells us that this particular cobalt is cobalt-59 isotope. So there's our nuclear reaction. Calculate the rate constant for the decay of iron-59 to cobalt. Okay, so that we're going to do with our T1/2 equals 0.693 over K. And we're calculating the rate constant K. So first thing we want to do is multiply both sides by K to get rid of it. And then we want to divide both sides by T1/2 to move that down. And now we're going to plug in our T1/2, our half-life, 45.1 days. So the rate constant for this, 0.693 divided by 45.1. The rate constant is 0.0154 inverse days. Moving on, how many half-lives will elapse as a 100% sample decays to 14.29%? Whew, that sounds tricky. Let's see if we can use this equation right here. So we're looking for an amount of time. We want to give that time in units of half-lives, but really we're going to start by solving just time. How much time will pass, and then we'll turn that into how many half-lives will pass. We don't know for sure exactly what N1 and N0 are, but we do know that our initial amount of iron is 100%. And our final amount of iron is 14.29%. So we can plug that into that natural log equation, and we know our value of the rate constant, negative 0.0154 inverse days. And then we can solve for time t. 14.29 divided by 100, take the natural log of that, and divide by negative 0.0154. So the time that has passed is 126 days. That is not really what the problem is asking. It wants to know how many half-lives that is. So we're just going to take that number of days and divide by the number of half-lives. 126 days is 8,204 half-lives. And again, I got that by taking 126 days and dividing it by the half-lives. Right on. So moving on to problem number 3, we have a rock, and it contains some uranium and some lead. And we're given the half-life of the uranium. And we need to, first of all, use figure 20.1. That's from an old edition. We're going to be using figure 20.2 to determine the stoichiometric relationship between the uranium and the lead. Let's go take a look at that figure. So here it is. And this figure starts, this is the decay series, so we're starting with the uranium-238. And we're just looking at the stoichiometry here. So 1 uranium converts to 1 thorium, to 1 Pa, to 1 U, 1 Th, etc., etc., etc. We're trying to get all the way down to lead. So it's a 1-to-1 relationship in this. There's never, you don't see a stoichiometric coefficient anywhere in this whole entire figure. So that's going to make this pretty simple for us. So the stoichiometric relationship between uranium and the 206 lead is 1-to-1. Determine the mass of uranium that must decay to produce 2.47 milligrams of lead. And determine the original mass of uranium and determine the rate constant. So, this is tricky. So we have uranium-238 that is converting into lead-206. And in this particular rock, we have 4.31 milligrams of uranium, and we have 2.47 milligrams of lead. And the question is asking how much uranium had to decay to give us this much lead. Well, we know that the uranium and the lead are a 1-to-1 ratio, and so we can do a lead to uranium conversion the same way we would do any sort of stoichiometry. So we're going to start by writing the 2.47 milligrams of lead. We want to convert that into grams. 1 gram is 1,000 milligrams. We want to convert out of units of grams and into units of moles. So we're going to do a gram of lead to mole of lead conversion. Looking at the periodic table, lead is 207 grams per mole. So how are we doing? We've gotten rid of the milligram unit. We got rid of the gram unit. We know that the uranium and lead are 1-to-1. So now we're into the units of moles of uranium. And now we're ready to convert out of moles of uranium, so I've got to carry my math down here, into grams of uranium. Looking at the periodic table again, uranium is 238. And then we probably are going to want to convert this back into milligrams, so 1,000 milligrams per gram. Moles cancel. And so we're going to get 2.47 divided by 1,000 divided by 207 times 238. 2.84 milligrams of uranium. Now that is how much converted into the lead. So if our rock currently contains 431 milligrams, and that's what's left after 2.84 converted itself into lead, the original mass is 4.31 plus 2.84 milligrams. 4.31 plus 2.83. The original mass is 7.15 milligrams. The 2.84, that is how much decayed to make 2.47 milligrams of lead. Now it wants us to determine the rate constant of the decay. So I think that for that, we're going to use the natural log of n1 over n0 equals negative k times time t, and calculate the age of the rock. The rate constant we want to get from the half-life. T1/2 equals 0.693 over k. The rate constant, we've got to rearrange this a little bit. The rate constant is going to be 0.693 divided by our half-life, 4.51 times 10 to the negative 4 inverse years. Again, that doesn't make sense. It's not inverse years, it's just years. So our rate constant is 0.693 divided by 4.51 times 10 to the minus 4, 1537 inverse years. That's our rate constant. And the age of the rock. The natural log of n1 over n0 equals negative kt. T is what we're trying to solve for. We just figured out k. This is the rate constant for uranium because it's based off the half-life of uranium. So what is our original or our initial mass of uranium? 7.15. And what do we have at this current time? 4.31. Rate constant, 1531. And we can solve for time. 4.3 divided by 7.15. Take the natural log, divided by -1537.